So here is an indefinite integral for you to calculate, and after you've had a go with pen and paper, you can come back and I'll give you a detailed solution, an exercise to check the solution by differentiation, and also a comment on an alternative that I've sometimes seen students use, which I do not advise. Okay, see you in a few minutes. Welcome back. Let's look at the answer to this exercise. So in the integrand here, we have got a factor of a square root cubed of 2 minus x squared. And this square root factor, something positive minus x squared, should make us think of a sign substitution. But we do not want to say that x is equal to sine theta. I'm going to write it, but I'm going to leave a bit of room in front of the sine theta, because if we were to do that, we would not have this square root factor as one of the sides of our triangle. So what we need is to have, for the side of the triangle here, the square root of 2 minus x squared. And clearly the sides of the triangle have to satisfy Pythagoras' theorem. So here we're going to put a factor or a length of x, because if we now square that, and we will get x squared, square this, we have 2 minus x squared, add them together, the x squared and the minus x squared will cancel and we will be left with 2. So the hypotenuse squared has got to be 2, and that means that the length of the hypotenuse is the square root of 2. And if you just pause and think about it for a second, you convince yourself that yes, these sides of the triangle satisfy Pythagoras' theorem. So the sine of theta is x over the square root of 2, and that means that x is equal to the square root of 2 times sine theta. And we're going to need the derivative, dx d theta, and that's going to be the square root of 2 times the cosine of theta. And if we needed theta at the end, which we're not going to, but theta would be the arcsine of x divided by the square root of 2. So you just divide x by root 2, x over root 2 is sine theta, theta is arcsine of x over root 2. It's helpful always to write down the formula that you are using. So we're saying you have some integrand, and you can rewrite x in terms of a shiny new variable that I'm calling theta. So you just rewrite the integrand in this way. Everywhere you have an x, you replace it by how it's defined in terms of theta. And then you insert by hand a factor of dx d theta, and that gives us a new and we hope doable integral in terms of theta. So concretely, we have 1 over, and now this is the square root cubed, and we just look at the triangle and we see that the square root of 2 minus x squared over root 2 is cos theta. So therefore we see that the square root of 2 minus x squared is equal to root 2 times the cosine of theta, just from looking at the triangle. You can also do it by saying, well, if I square x, I will get 2 times sine squared theta, and if I put it into the root, I would have 2 minus 2 sine squared theta. So that's 2 times 1 minus sine squared theta, 2 times cos squared theta. Take the square root, and bear in mind the way theta is defined as an arcsine, the cosine is always positive. Okay, much easier just to draw the triangle. So now, 1 over the square root cubed is, we've said, root 2 cos theta, all cubed, cubing the root 2 as well. The dx d theta factor is also root 2 cos theta. So we have a root 2, and we have 3 powers of root 2 in the denominator. That will cancel with one of the 3. You'll be left with root 2 squared. That's a factor of a half, which I've just pulled out front. Here we have cosine over cosine cubed. That is 1 over cosine squared, or secant squared. And we hopefully remember that the derivative of tangent is secant squared, so therefore the integral of secant squared is tangent. So that is our answer for the integral in terms of our new variable. And again, you could use algebra. Tangent is sine over cosine, so it is sine over the square root of 1 minus cosine squared, etc., etc. Or we just look at the triangle. Tangent is opposite over adjacent, so it is x over the square root. And don't forget the half that's sitting there in front. And that is our answer for the integral. So what did we do? We've just made a sign substitution, and the point about this exercise is just to start exploring how having numbers other than 1 inside our square root change things. And you can see it's just a small change, and that drawing a triangle and verifying that one of the sides of the triangle is the root that's causing the issues tells us that this is the correct substitution to use. Okay, let's now check this by differentiating it, and actually what I'm going to do is I'm going to give you that as an exercise. Let's look now at the next slide. Okay, so as I've said, verify this by differentiating our result for the integral and seeing that you obtain the integrand. And the way I would do it is I would view this as x multiplied by 2 minus x squared to the power of minus a half, and use the product and chain rules. Now, just to finish off this video, I would like to ask a question. Could we use a cosine substitution? I've sometimes seen students do this. And the answer is in principle yes, but don't do it. There is absolutely no reason for doing it. So let me just try to sketch what you would do very quickly. You draw a triangle like this, and you say, okay, I'm going to say that the cosine of theta is x over root 2 instead of the sine. That means this side of the triangle is our square root, and we think, well, this certainly seems to be working. And dx d theta is minus root 2 sine theta, because when you differentiate cosine, you get minus the sine. And otherwise, it just carries on as before. But actually, this swapping the sides around gives nothing additional. It does not allow us to do integrals that a sign substitution wouldn't do. And you get an extra minus sign. And we've all made mistakes with minus signs. So why on earth would you want to try to tackle a problem in a way that you have an extra minus sign? It's just an additional way of making a mistake, and it does not allow you to calculate any integral that a sign substitution wouldn't do for you. So please don't do this. Okay, with that, I'll stop the video.